ever stop to think about what's really going on in the air all around us? It feels like nothing, right? Just empty space. Well, today we're diving deep into the secret life of gases, uncovering a hidden world of chaos and speed that explains, well, everything from the air we breathe to how our world works. Okay, let's start with a puzzle you see every single day. You've got a 2-ton car that's thousands of pounds sitting on 4 rubber tires filled with air. Just air. So what's going on in there? What invisible force is holding up all that weight? To answer that, we have to look inside the tire. And what we'd find isn't calm, empty space. It's more like a constant, raging, invisible storm. See, the thing holding that car up isn't a static substance. It's the combined, relentless force of trillions and trillions of tiny particles all moving at insane speeds, constantly slamming into the inside walls of that tire. It's an endless barrage. So how in the world do we get our heads around this invisible storm? To really unlock this, we need a kind of master key. And nobody described this key better than the physicist Richard Feynman. Feynman once argued that if you could only pass down one sentence of scientific knowledge to future generations, this should be it. The idea that everything, you, me, the air, everything, is made of tiny particles that are always moving is without a doubt one of the most important ideas in all of science. And that's the atomic hypothesis. This is the clue that unlocks everything for us. The moment you accept that the air in a tire isn't just nothing, but a massive swarm of constantly moving atoms, you're on the path to understanding how it all works. Now, to make sense of all this chaos, physicists came up with a simplified model. They call it an ideal gas. Just imagine a huge number of tiny particles so far apart there's mostly empty space between them. They're all moving randomly and bouncing off each other like perfect little billiard balls, never losing any energy. Now look, it's a simplification for sure, but this model is incredibly good at predicting how real gases behave. So let's use this model. Let's connect that tiny microscopic action to the things we can actually see and measure in the real world, like pressure and temperature. Okay, so what is pressure when you zoom all the way in? It's not some steady, even push. It's the average force from what is essentially high-speed machine gun fire, with trillions of molecules slamming into the walls every single second. And of course, physics gives us a neat little equation for this. Now, don't worry about the math here. The big takeaway is that pressure, that's P, really just boils down to 3 things. N, how many molecules you've packed into the space, M, how heavy each one is, and V squared, which is the really important one, how fast they're moving. More particles or faster particles means more collisions, and boom, more pressure. Simple as that. All right, that makes sense for pressure. But what about temperature? When you say the air is hot or cold, what's actually happening on that molecular level? This is the best part, because it's so beautifully simple. Cold just means the molecules are, on average, moving pretty slowly. Hot just means they're moving much, much faster. That's it. It's all about motion. So you can think of a thermometer as basically a speedometer for molecules. It's not measuring some weird abstract thing called heat. It's giving you a reading of the average kinetic energy, the energy of motion, of those atoms. When you heat up your coffee, all you're really doing is making its atoms jiggle and dance around faster. So we know that temperature is all about this energy of motion, but you've got trillions of particles. How is that energy actually shared between them? This leads us to another really elegant idea, a law that governs how energy gets distributed. It's called the law of equipartition of energy, which is a fancy way of saying that nature is fair. It says that once a system settles down, the total energy budget gets shared equally among every possible way a molecule can move. Every mode gets its fair share of the energy pie. So what are these ways to move? Well, think about a molecule of oxygen in the air. It can move from point A to point B. We call that translation. It can also spin around like a top. That's rotation. And the 2 atoms can even vibrate back and forth like they're connected by a tiny spring. Each one of those is a degree of freedom, a way to hold on to some energy. And here is the amazing part. The law actually tells us what that equal share is. Each degree of freedom, on average, gets this tiny amount of energy, 1/2 kBt. T is just the temperature, and kB is just a fixed number to make the units work out.
It's this incredibly simple and powerful rule that lets us predict exactly how gases will behave. All right, for our last big idea, let's dig into a really fun paradox. We know these molecules are moving incredibly fast, but our everyday experience doesn't seem to match up. Seriously, think about this. A typical air molecule is zipping around at the speed of a jet airplane. So if someone opens a pizza box on the other side of the room, shouldn't you smell it instantly? Why does it take a minute for that smell to drift over to you? The answer to this puzzle has a great name. It's called the mean free path. The idea is that it's not about how fast a molecule is going, it's about how far it can get before it smashes into another one and gets knocked off course.
So that molecule carrying the delicious smell of cookies isn't making a straight line dash for your nose. Not even close. It's on a completely chaotic, random walk. It goes super fast for a tiny distance, collides, goes a different direction, collides again, and so on billions of times.
And to put a number on it, for a molecule in the air around you right now, the average distance between collisions is only about 100 nanometers. That's microscopically small. But here's the wild part. That tiny distance is still about 1,500 times bigger than the molecule itself. So from its perspective, there's a ton of empty space. But there are just so many other molecules that collisions are constant. So let's just recap what we've pulled back the curtain on. We've seen that what looks like empty space is actually a raging storm of atoms. We've learned that pressure is just the force of their constant collisions, and temperature is just a measure of their speed. And finally, we know that their journey from one place to another isn't a straight line, but a long, chaotic, zigzagging path. By understanding this secret life of gases, we've taken something as simple as air and seen it for what it is, a dynamic, complex, and beautiful system. It really makes you wonder, doesn't it? What other invisible forces, what other secret dances of tiny particles are shaping our world in ways we can't even begin to see?